let's say we want to take the integral of the square root of 25x squared minus 4 all over x. So before I introduce the new concept I want to introduce in this video, let's check if we can take this integral with any of our techniques that we know already. So first, let's see if we can take this maybe using just anti-power rule. And then we're going to resort to u substitution, and then we notice that it looks like we can do this problem with u substitution, so let's try it out. If we let u equal 25x squared minus 4, and we subtract, or sorry, we find du, well, du would be 50x dx. We notice that we cannot use u substitution because the x is on the bottom, right? So if we have 50x dx on top, it doesn't work. We need this to be on the bottom, and that means we have to divide by du, which doesn't work. So we cannot use u substitution. So this is where something called trig substitution comes into play. Now, before I tell you how I got this value that I'm about to use, just watch the video and I will tell you that at the end. I want to first do it with just this value that I already know, and then after I will tell you how I got this. So we're going to let x equal 2/5 secant theta. So we're going to say that x is equal to 2/5 secant theta. So we're going to make a substitution for x. And well, we know that dx, well, dx has to be just 2/5. The derivative of secant theta is just tangent theta secant theta. So 2/5 tan theta secant theta. Now, let's substitute the values that we know. And then this is d theta. All right. So let's do that. So we know that x is 2/5 secant theta. So let's substitute those values in. So we get the integral of the square root of 25 times 4/25 secant squared theta minus 4 all over x, which is 2/5 secant theta, and then we have to multiply by dx, right? So we can't forget that. And dx is this whole thing here. So times 2/5 tan theta secant theta, and then d theta. Okay, so we have a lot of simplification to do, so let's think about this. Before we do any of that, we need to recall this identity. We know that tangent squared theta plus secant squared theta actually, that is not the identity. Tangent squared theta plus 1 is equal to secant squared theta. So this is a very fundamental and important trig identity that we should recall from pre-calculus and maybe calculus. So tan squared theta plus 1 is equal to secant squared theta. So let's see if we can possibly get this right here into the format of this right here. And if we could, that will help us. So we have our, actually let's simplify the square root first. So we're left with the integral of the square root of 25 over 25 cancels, right? We get 4 secant squared theta minus 4, so we can factor out of 4. So I get 4 times secant squared theta minus 1. And if you're stuck on how I did that, just pause the video and do some algebra to simplify this. And then for this, we can cancel out the 2/5 secant theta. And so we're just left with tan theta on top, d theta, right? So we're left with times tan theta d theta. Okay, this is looking good. A lot of things have simplified already. Now, let's use this identity to our advantage. We know that if we subtract 1 on both sides in this identity, we get tan squared theta is equal to secant squared theta minus 1. And right here we have secant squared theta minus 1. So let's substitute that. So we're left with the integral, the square root of 4 tan squared theta, right? This is completely equivalent, times tan theta d theta. So to me, it seems like the integral is becoming possible pretty soon. So let's keep going. This is equal to, well, the integral of, we can simplify 4 tan squared theta to just technically the absolute value of 2 tan theta. We're gonna just drop that for now. So we get the integral of 2 tan theta times tan theta, right? So 2 tan squared theta d theta. Okay, this is looking good. This is looking really, really good. Now, again, let's use our identity. We know that our identity says that tan squared theta is equal to secant squared theta minus 1. So let's take the 2 out and use our identity. I'm going to go up there. So we can rewrite that as an integral as 2 times the integral of, well, secant squared theta minus 1 d theta. And we know that the integral of secant squared theta, that's just tan theta, right? Because the derivative of tan theta is secant squared theta. So we're left with 2 tan theta. Oops. So we're left with 2 tan theta minus 2 theta. And there are no bounds, so we need a plus c. So we did take the integral of this, but it looks a little weird because it's in terms of theta. So we didn't quite take the integral of this in terms of x. So is there any way for us to replace this perhaps and write it in terms of x? And the answer to that is actually yes. But it's a bit indirect. So we need to do something before we can replace any of the thetas with x. We first need to get theta in terms of x. And to do that, we actually need to draw a right triangle. Well, let me show you why. So let's draw a right triangle. And we know that x is equal to 2/5 secant theta, right? And therefore secant theta, let me show you here. So therefore secant theta, so I'm going to write that right here, is equal to 5x over 2, right? I just solved for secant theta from this equation here. So if this right here is theta, and this is our 90-degree angle, we can say that the secant of theta is 5x over 2, right? So therefore the cosine of theta has to be 2 over 5x, right? Because secant theta is equal to 1 over cosine theta. And for that reason, cosine of theta has to be 2 over 5x. Therefore, this has to be 2, and this has to be 5x. Right? If we take the cosine of this angle, or if we take the secant, we get these expressions, equations. So that's good. Now, we, however, want tan of theta, right? We want tan of theta, and then we also want theta in terms of x. Well, we can already get theta in terms of x by taking an inverse here. So we can get theta is equal to cosine inverse of 2 over 5x, right? We can solve for theta from any of these equations by taking an inverse. So theta is equal to cosine inverse of 2 over 5x. So that's good. We got that. We just need tan theta now. Well, we can get tan theta if we know this side, right? Whatever, because if we get this side over this side, that's tan theta. So let's find that side. And we can find that side by using the Pythagorean theorem. So we get 2 squared plus that side squared, which I'll call h. Again, it doesn't matter what variable you use. Let me write this a little better. So 2 squared plus h squared. Again, this is a long problem, but we're almost done. 2 squared plus h squared is equal to 5x squared. So 25x squared. So h has to be the square root of 25x squared minus 4. That's interesting. 25x squared minus 4, right? Now, tan of theta is h over 2, right? So let me write that right here. So tan of theta is the square root of 25x squared minus 4 over 4. Okay. Now, let's see. So we got that value. Actually, sorry. 25x squared minus 4 over 2. Sorry. All right. Now we can just substitute those values in here to write our final answer. So I'm going to write it right here. I'm going to try to squeeze it in. So we know that 2 times tan theta, well, the 2's cancel, and we're left with the square root of 25x squared minus 4 minus 2 cosine inverse of 2 over 5x, all plus c. And I still didn't tell you how I chose x equals 2/5 secant theta, but I think it should be a little bit more clear now. So the reason why we chose that is because we know this identity, and we were trying to get inside the square root to have an expression that looks like this. And to do that, we need to choose something very specific to cancel out the 25. So 2/5 secant theta would be the right choice. And you get much better at choosing values for x with trig substitution with practice. So our final answer is the square root of 25x squared minus 4 minus 2 cosine of inverse of 2 over 5x plus c.